Now today that will be our last class on the momentum transfer. In this class we will try to have an understanding of this turbulent flow behavior. That means how the different quantities which are associated with the turbulent flow, how those quantities can be measured statistically, and how the Reynolds stress can be evaluated in order to have an interpretation of the molecular momentum transfer. So, this is our 19th class or the ultimate class of this momentum transfer, EP19, in which we will study the turbulent flow behavior. So far as the turbulent flows are concerned, this is of immense importance in the metallurgical engineering. The flow of the liquid metal and the slag either from the blast furnace or the other furnace which is being utilized for the extraction of metal from its ore. These travel of this liquid metal and alloy generally follows the turbulent flow conditions, and henceforth it is necessary to have a manifestation of this turbulent flow behavior. So, generally for pipe flow, if the value of the Reynolds number is lesser than 25, then it can be said that the flow is laminar. However, if the Reynolds number is greater than 25, then it is said that flow is turbulent, right. So far as these macroscopic aspects of the turbulence is concerned, so the macroscopic aspects of turbulence. While discussing the friction factor, I have mentioned one statement, if you might have remembered that if any surface which seems to be a flat surface through the naked eye, if you examine the same surface in a microscope, either in the compound microscope or even the high resolution microscope such as scanning electron microscope, you will find that there are so many undulations are there on the surface which was initially seems to be a flat surface. On the very same guideline, for the fluid flow condition in which a constant velocity, average velocity is there, it seems to be that the constant average velocity is there, but if you examine that flow on a macroscopic level, then you will find that even in the laminar flow also there are so many undulations in the velocity. Henceforth, it is necessary to have an idea about the time average value of such components to have a better understanding of the turbulent flow in many circumstances. As previous in the previous class, I have told you that the utilization of the Argun equation to take part of the laminar and turbulent region at the high flow rates is very necessary to establish, to have the correct value or exact value of the pressure drop in the industrial practices, but usually it does not happen. It does not happen because that at many places the correct equipment for the measurement of such things are not there, or the correct assessment is not possible due to these restrictions. So, on the same guidelines, if even for a steady state situation, if you examine the turbulent flow, if you examine a flow, let us suppose this is along the x-axis, I am putting here time, this is Vx, this is oscillogram. Let us suppose this is your average value of velocity, this is suppose the V average, okay. Let us suppose this is the average value Vx. You will find that so many fluctuations are there in this manner. So many fluctuations are there in this manner. This is called your Vx dash, that is the local fluctuation the velocity Vx dash. So above oscillogram describes that even for a steady state condition, that is V average is equal to a constant, there is appreciable fluctuation in velocity with respect to time. So Vx, this is an oscillatory function of time. It is an oscillatory function of time. And in x direction, the time average, this diagram you can say this figure is time average fluctuating velocity component in turbulent flow. So Vx is an oscillatory function of time. In x direction, the time average value of velocity component, can be given as Vx, that is equal to 1 upon T naught integration from 0 to T naught Vxt dt. Vx is a function of T, that is into dt. Let it be question number 1. T0 is the length of time which is much greater than the frequency of turbulent oscillation. So this is the representation. Question 1 is nothing but it is representation of the average velocity that means the integration of the Vx dt divided by T naught, integration over the limit 0 to T naught. So, also the instantaneous velocity, the instantaneous velocity, that is the Vx, the instantaneous velocity Vx, that should be equal to average value of Vx plus this fluctuation, that is the Vx dash. Let it be question number 2. Vx dash is the fluctuating component of velocity, fluctuating velocity component. Also, Vy is equal to Vy average plus fluctuating Vy, and talking about the Vz, that is the average value of Vz plus fluctuating Vz component. Similarly, on the similar guideline, the fluctuation in pressure, that means the pressure created due to the difference in velocity during the flow of turbulent nature. So, this fluctuation in pressure can be represented as that is P equal to average value of P plus fluctuation in pressure P dash. By definition, I am giving you the ideas about the term associated with the turbulent flow and how these things can be measured if you have an oscillogram with you. Oscillogram is nothing but, oscillogram technique is nothing but this is a statistical method to evaluate such things through the integration. So, the numerical method. So, by definition, time average value of fluctuating component, that is an approximation, fluctuating component that is equal to 0. That is Vx prime average, that is equal to 1 by T naught integration from 0 to T naught Vx prime dt, that should be equal to 0. Similarly, on similar guidelines, Vy dash, that is equal to 1 upon T naught integration from 0 to T naught Vy dash dt, that should be equal to 0. Similarly, average value of Vz prime, that is equal to 1 upon T naught integration from 0 to T naught Vz prime dt equal to 0. So, this is equation number 6, 7 and 8. However, time average value of square of fluctuating component is not 0. This you should keep in mind. Time average value of the square of the fluctuating component is not equal to 0. That means, if I am saying that average value of Vx dash square, that is equal to 1 by T naught integration from 0 to T naught Vx prime square dt, that should not be equal to 0. Let it be question number 9. So from the above discussion, the quantities which is used to represent a turbulent flow thus the quantities which can be utilized to represent turbulent fluctuations are, the quantities are Vx prime is square, average of this quantity, divided by Vx dash, Vy prime square average divided by Vy prime, divided by Vz prime square average divided by Vz prime. These quantities can represent the turbulent fluctuation, and also the intensity of turbulence also, and the intensity of turbulence may be evaluated as the capital I, that is equal to 1 upon average value of Vx into 1 by 3 average of Vx prime whole square plus average of Vy prime square plus square of average Vz prime whole raised to the power half. Let it be question number 10. Another important thing in the turbulent behavior is the Prandtl mixing length model. That is our last topic of the present momentum transfer study. So let us try to discuss this Prandtl mixing length model. Prandtl mixing length model. The next topic and the last topic of today's class, Prandtl mixing length model. Apart from the time averaged equations and boundary layer theories, Prandtl mixing length model is also a tool, to explain the momentum transfer. In order to have an understanding of this momentum transfer by utilizing this Prandtl mixing length model, the first and foremost task is the evaluation of the Reynolds stresses. So, this Prandtl mixing length model is also a tool to explain the momentum transfer. This model is based on the evaluation of Reynolds stresses, through the use of ED viscosity, principles. Newton's law for the laminar flow is tau Ix is equal to minus mu dVx by dy. Let it be question number 11. And for turbulent flow, the equation is tau Ix in the turbulent condition, that should be equal to minus mu t dVx. Now it is customary to take the average value, so dVx by dy. Here mu t is called the turbulent viscosity. And this is a function of position and flow, whereas viscosity is a fully flow property. So, this equation number 12 can be rewritten as tau Ix for the turbulent condition, that is equal to minus rho into epsilon t, as we have obtained the case of the Newtonian fluid, that is minus mu dV by x by dy, that is equal to written as minus mu into rho. So, here also rho and mu is replaced by the epsilon t, that is called the turbulent diffusivity or ED momentum diffusivity, rho into epsilon t dVx bar by dy. Let it be question number 13. Here this quantity epsilon t is equal to mu t upon rho, that is called the ED momentum diffusivity. This is called the ED momentum diffusivity, and similar to mu by rho in the cases of laminar flow. In the cases of laminar flow. Now, this Prandtl mixing length model has certain assumptions. Those assumptions are the assumptions which are lying in the Prandtl mixing length model. The assumptions: number 1, it is formed in turbulent flow behave as if it is a gas and loosen its identity after moving through a distance, let the distance L, distance may be abbreviated as L, this distance after which the ED completely lost its identity, that length is called Prandtl mixing length, This length is called as Prandtl mixing length. And the second assumption is that the fluctuation in the velocity in both the direction x and y are equal. And the second assumption associated with the Prandtl mixing length model is that fluctuation in velocity Vx is due to the lump of fluid moving in x direction, moving in y direction. Fluctuation in the velocity Vx is due to the lump of the fluid moving in y direction. Now, this movement can be examined through this representation. Let it be, this is the x-axis, this is the y-axis, this is the true velocity, this is the fluctuation in Vx, average value of Vx at a distance y equal to y plus L, and this is the average value at the value y equal to y. Now, let is the fluid velocity at y equal to y, and this is the velocity of fluid at y equal to y plus L. So, the fluctuation in velocity fluctuation in velocity, that is equal to Vx dash in the direction of y, that will be equal to average value of this fluctuation at the value y equal to y plus L minus average value of fluctuation at y equal to y. So, you can write Vx prime at y divided by L, that is equal to Vx prime average at y plus L. Wait. Here this should not be prime. Sorry, you are missing the prime, so the fluctuation in the average velocity. So this only. So Vx at y plus L minus value of average Vx at y equal to y divided by L, or we can write fluctuation in the Vx at y equal to y, that is equal to L into this, that can be written as L, that can be written as L dVx average by dy, because L is the length of the y direction, so this dy, and this quantity Vx prime at y equal to y, that may be written as also Vx dash equal to this. Also Vy dash equal to L dVy divided by dy. Let it be question number 14. Let it be question number 15. Now, Prandtl, by assuming small velocity fluctuations and assuming that the Vx dash equal to Vy dash, so the time averaged Vx dash Vy dash can be given as Vx prime Vy prime, its average value, that will be equal to minus L square mod dVx by dy into dVx by dy, dVx average by dy. Let it be question number 16. Here the negative sign and the absolute value both are used for making the quantity Vx prime Vy prime average in agreement with the experimental data, in agreement with the experimental data. In order to make this quantity in close agreement with the experimental data, both the negative sign as well as the absolute the modular sign has been utilized here. So, the Reynolds stresses, such as tau xx turbulent, its average value, that will be equal to rho Vx prime that is equal to this. Similarly, if I am assuming the tau yx turbulent Reynolds stress, that is equal to Vy prime Vx prime, this average, tau zx in turbulent condition, that will be equal to rho Vz dash Vx dash, its average value. Let it be question number 17. So, let us take the value of this representative value, this Reynolds stress. So, tau yx average value in the turbulent condition, that will be equal to rho into this quantity L square, that is minus dVx by dy modulus into dVx by dy. Let it be question number 18. Thus, from equation number 12 and 18, thus from equation 12 and 18, refer the equation number 12 and 18, we can write, just from equation number 12 and 18, we can write what we can write. We can write that minus rho into epsilon t, that should be equal to minus rho L square modulus of dVx by dy, dVx average by dy into dVx average divided by dy. So, from this value the epsilon t comes as minus rho epsilon t into dVx average by dy, that should be equal to minus rho this. So, the value of epsilon t comes as L square dVx bar by dy. This is the expression for the Prandtl mixing length, which can be used to evaluate the Reynolds stresses, and hence it can be used to provide a mechanism for the molecular momentum transfer. So, dear students, this ends for your course so far as the momentum transfer is concerned. So, you can write here the equation number 19. Equation number 19 is the expression for ED momentum diffusivity, ED momentum diffusivity, and the Prandtl length, EG momentum diffusivity and Prandtl length. So, this completes your momentum transfer. From the next class, we will start the heat flow analysis, the heat transfer, the various concepts of heat transfer, and we will start from the radiation heat transfer first. After that, I will take up the conductive heat transfer. Thank you so much.